Hello everyone, my name is Nidhi Singh. I am assistant professor in Gyan Vihar School of Pharmacy, that is a part of Suresh Gyan Vihar University, Jaipur. Today we are going to discuss this topic, carboxylic acid, which is in pharmaceutical organic history first. So here we are going to discuss that what are the carboxylic acids derivatives and how we can nomenclate them and what are the relative stabilities. So in this, the learning objective is that we are going to discuss about the carboxylic acid derivatives, and also we are going to study about the structures and the ionic nomenclature of carboxylic acid derivatives. And here we are going to study about the relative stability of SI derivatives. So in this we are going to study today's topic. In this we are going to study about the carboxylic acid derivative, the structures and the ionic nomenclature of carboxylic acid derivative, their relative stability of acyl derivatives, and the student outcome is that they are going to know about carboxylic acid derivative, means what is the carboxylic acid derivative, and what is the structure of this carboxylic acid derivative, and how we can nomenclate it, means we can give naming according to the IUPAC system of carboxylic acid to these carboxylic acid derivatives. And also we are going to learn about the relative stability of acyl derivative, means here we are going to study about the relative stability of these acyl derivatives. So let's start the topic. So in this, the most important derivatives of carboxylic acid are acyl chlorides, acid anhydrides, esters. There are and are dash maybe some or different, and amides are SGVU, which are obtained by the replacement of OH part of carboxylic group of acids by Cl, OCO, ROR or NH2 group respectively. So in this carboxylic acid derivative, as we know that the carboxylic acid structure is the RCOOH. So in RCOOH, if there is a replacement, then it becomes the carboxylic acid derivatives. So in this case, they are formed. How they are formed? So here the important carboxylic acid functional groups are your acyl chloride, acid anhydride, esters, amides, and these can be obtained by the replacement, means in the carboxylic acid, the hydroxyl part that is attached to the carbonyl part is replaced, have been replaced by these Cl, OCO, ROR, NH2 groups. So here you can see that this is the carboxylic acid, which is a mixture of this carbonyl group plus the hydroxyl group, and in this the hydroxyl group is replaced by the. So here you can see the OH is replaced by OH is replaced by Cl. OH is replaced by Cl, and after that there is a formation of this acid chloride, and then carboxylic acid is the acid chloride is formed by the replacement of OH by the chlorine. There is a formation of this acid chloride. After that, this OH group is replaced by this acyloxy group, acyloxy. Then there is a formation of this acid anhydride, and this OH group is replaced by the carboxy group, that is your OR. Then this is your ester, and if this is OH group is replaced by your NH2 part, then it is your amide. So here, this carboxylic acid derivatives are formed by the replacement by these functional groups, and in this carboxylic acid, As you know that carboxylic acid is having both the carboxylic carbonyl part and the hydroxyl, means it is made up of this carbonyl group as well as this hydroxyl group. So here both of them are by the both of them are formed if both the carbonyl group and the OH groups are attached to this carboxylic acid, then they form the carboxylic acid. And if the OH group is replaced by this Cl, then there is the formation of this acid fluoride. And if this OH is replaced by the acyl oxide, then there is a formation of this acid anhydride. And if OH group is replaced by the alloxyl, then there is a formation of this ester. And if OH is replaced by NH2, then there is a formation of this amide. So this is the introduction part in which the important functional groups of carboxylic acid are your acyl fluoride, or your acids anhydride, means your acid and fluoride, and acid anhydride, esters. And in esters, the two are alkyl groups are attached, and it can be different also. If both can be same, if both are can be your alkyl group, or one is your alkyl and the second is your acyl group. And amides, and which are obtained by the replacement, of OH part of carboxyl group of acids by Cl, OCOR, OR, and NH2 group. So here these carboxylic acid derivatives are formed by the replacement of your OH part from the carboxylic acid, and there's a formation of this four type of carboxylic acid derivatives. Next is the structure and the nomenclature of acid fluoride, acid anhydride, esters, amide, and anhydride. So the structure and the nomenclature means what is the structure of this carboxylic acid derivative, and how can we nomenclate? How can we nomenclate? Means how can we name these acid fluoride, acid anhydride, esters, amide, and anhydride? So a carboxylic group contains a carbonyl group and a hydroxyl group bonded to the carbonyl carbon. So in this, a carboxyl group contains a carbonyl group and a hydroxyl group bonded to the carbonyl carbon. The structure of carboxyl group is like this. So here the carboxyl, as I have told you, that the carboxyl group contains a carbonyl group as well as a hydroxyl group is bonded to the carbonyl carbon. So this carbon is having the both functional group, that is your carbonyl group, as well as your hydroxyl group that is bonded to this carbonyl carbon. And the structure of carboxyl group is is COOH. So the C is having the sp2 hybridization, because you can see that C is 1, 2, 3, 1, 2, 3. So here this carbon is your sp2 hybridized. So the carboxyl group in a carboxyl, the carboxyl carbon in a carboxyl acid is bonded with three functional groups. Therefore, the carboxyl carbon is sp2 hybridized. Means from one part it is attached to OH group, and from second functional group is your oxygen, and the third is your alkyl portion. So here that is why this carboxyl carbon is your sp2 hybridized, and hence the carboxyl group has a planar structure with bond angle of approximately 120 degrees, and the carboxyl acid derivatives are the original compounds that are synthesized from the carboxyl acid by the replacement of OH group of carboxyl group by Cl, OCOR, OR, and the NH2. So here, what is the structure of this carboxyl acid derivative? So it can be the structure of these carboxyl acid derivatives can be obtained from the structure of the carboxyl group. So the carboxyl acid group contains a carbonyl group, the CO part, and the hydroxyl group, the OH part, that is bonded to the carbonyl group, carbon. So this CO and this hydroxyl group is bonded to the carbonyl carbon, and the structure of the carboxyl group is like this. So here in this part, this C is a sp2 hybridized because it is attached to the three function group. That is, one here is your alkyl group, second is your oxygen, and the third is your OH group. So the carboxyl carbon, this carboxyl carbon in a carboxylic acid is bonded with three function groups, 1, 2, and 3. Therefore, the carboxyl carbon. So this carboxyl carbon is your sp2 hybridized, and hence the carboxyl group has a planar structure. So this carboxyl group has a planar structure and is having a bond angle of approx 120 degree. So this carboxyl group has a planar structure. So due to and its bond angle is approximately 120 degree. So the carboxyl group is planar because the carboxyl carbon is sp2 hybridized. That is why this uh, this carboxyl group is having a planar structure and is having a bond angle of 120 degrees. And the carboxyl acid derivatives are the organic compounds. So these carboxylic acid derivatives, these are the organic compounds that are synthesized. They are synthesized from the carboxyl acid. They are synthesized from the carboxyl acid by the replacement of hydroxyl group from hydroxyl group of carboxyl group, replacement of OH group of carboxyl group by Cl, that is a fluorine. If fluorine is replaced, then it becomes acid fluoride. OCOR means here it becomes your acid anhydride, that is your acyl oxy group. And third is your ORS gas, that is your alloxy group. And this or NH2 group, that is your NH2 group. So here the structure and nomenclature. This is the structure. Next, sorry. So here you can see this carboxylic acid is having this Z. If this Z is replaced, it is replacing this OH group, and it becomes a carboxylic acid derivative. So where Z may be chlorine atom, ethyloxy group, alloxy group, or amide group. So the four important carboxylic acid derivatives are acid chloride, acid anhydride, esters, and amides, and these acid and derivatives are distinguished from each other by the group attached to the carbonyl carbon atom. So here, this carboxylic acid is from this carboxylic acid, the Z means here the other functional group. It can be any functional group, that is, it can become chlorine atom, or it can be acyl oxy group, it can be alloxy group, or amide group. So here, this Z is the replacement of this OH, means OH is removed from here, and in its position, the Z is attached to the carboxyl acid. So it becomes carboxyl acid derivative. So here, where Z may be chlorine atom, acyl oxy group, alloxy group, or amide group. So the four important carboxylic acid derivatives are acid chloride, acid anhydride, esters, and amides. So these acid derivatives are distinguished from each other by the group attached to the carbonyl carbon atom. So as the structure of this carboxyl acid, it is containing the carbonyl group and the hydroxyl group bonded to this carbonyl carbon. The structure of carboxylic acid is this, and the carboxyl group in a carboxyl carbon in a carboxyl acid is bonded with three functional groups. Here it is bonded with three functional groups. Therefore, the carboxyl group, a carboxyl carbon, is your sp2 hybridized. And hence, the carboxyl group has a planar structure with bond angle of approximately 120 degrees. So, because of the carboxyl carbon, which is having the three functional group bonded to it, due to which it is your sp2 hybridized and sp2 um, hybridized, and hence the carboxyl group has a planar structure with bond angle of approximately 120 degrees, and the carboxyl acid derivatives, these carboxyl acid derivatives are the organic compounds. These are synthesized from the carboxyl acid by the replacement of OH group of carboxyl group by Cl, OCO, OR dash or NH2. So here, and after that, in this carboxyl acid, there is a replacement of. So here the example is given, means that is considered that it can be a chlorine atom, alkoxy group, and the alkoxy group or amide group. So it is replacing this OH part. It is replacing this OH part from here, and there is a formation of this carboxylic acid derivative. So this Z is the replacement of this OH group, and there's a attachment or the bond. It is bonded to this CO carbonyl part, and there is a formation of this carboxylic acid derivative. So here, where Z may be chlorine atom, alkoxy group, alkoxy, ethyloxy group, alkoxy group, or amide group. So, uh, so the four important carboxylic acid derivatives. The four important carboxylic acid derivatives are your acid chloride, acid anhydride, esters, and amides. So the carboxylic acid derivatives are acid chloride, acid anhydride, esters, and amides, and these acid derivatives are distinguished. These acid derivatives are distinguished from each other by the group attached to the carbonyl carbon atom, that is your acid chloride, acid anhydride, esters, or the amides. So these are the structure of this carboxylic acid derivative. So here in the acid chloride, you can see the Cl is attached to this RCO, and in this anhydride, acid anhydride, you can see this to this carboxyl part RCO, this OCOR is attached, that is your acyl oxide. And next is your RCO, this OR is attached, that is your esters. And in the case of amide, this NH2 is attached to this RCO. So here there is a formation of this carboxyl acid derivatives from this carboxyl acid. From there, this Z is the replacement, that can be any that may be chlorine atom, ethyloxy group, alkoxy group, or amide group. So from that, there is a formation of this carboxyl acid derivatives, and due to which there is a formation of these carboxyl acid derivatives. Next, hence the carboxyl acid and their derivatives contain a sp2 hybridized carbonyl group, which consists an O atom bonded to a C atom by a double bond in a planar module with bond angle of approximately 120 degrees. And in carboxyl acid derivative, the heteroatom group, that is a Cl, N, or O, is connected to the carbonyl group carbon by a sigma bond, and the resonance interaction of the carbonyl group with the lone pair of the adjacent atom has important implication on the reactivity. So the carboxyl, so hence the carboxylic acids and their derivatives, so the carboxylic acid and their derivatives contain a sp2 hybridized carbonyl group. This carboxylic acid and their derivatives contain a sp2 hybridized carbonyl group, and it is consisting of an O atom. So it is consisting of an O atom. O atom is your oxygen atom that is bonded to the carbon atom. So this oxygen atom is bonded to the carbon atom with the double bond, in a planar model with the bond angle of approximately 120 degrees, and because this is having the double bond, so here it is bonded to the um, it is having a planar structure, and it is having the bond angle which is approximately 120 degree. And in carboxyl acid derivatives, the heteroatom group, that is a Cl, N or O, is connected to the carbonyl carbon by a sigma bond. So this heteroatom group, that is your Cl, chlorine, nitrogen, oxygen, are connecting to this carbonyl carbon by a sigma bond, and the resonance interaction. So the resonance interaction of the carbonyl group with the lone pair of the adjacent heteroatom has important implication on the reactivity. So they are having a so the resonance interaction. So this is having the carboxyl acid is having a resonance interaction. So here the resonance interaction of the carbonyl group. So here the oxygen is having the lone pair, that is why there is a resonance interaction. So here the resonance interaction of the carbonyl group with the lone pair of the adjacent. So here the lone pair of the adjacent and the heteroatom means here this nitrogen is also having a lone pair, this oxygen is also having a lone pair. So there is a interaction of the resonance interaction of this carbonyl group with the lone pair of these atoms, these heteroatoms, which shows important implications on the reactivity. So on the reactivity, they are showing the uh, implications on it. Next is your the polarity of carboxyl acid derivative. So here structurally the carboxyl acid and the derivative differ by only the substituent Z attached to the carboxyl carbon as shown in the structure, and the carboxyl acid and the derivative have a common group, that is your acyl group. The chemical reaction of those organic compounds containing an acyl group depend on the nature of bond, that is of polar or non-polar, between the carbonyl carbon of acyl group and the substituent attached to it. In the organic compound containing an acyl groups are called acyl compounds, and on the basis of polarity, acyl compounds can be classified into two types, that is the non-polar carbonyl compound and the polar acyl compound. So in the polarity, so the polarity of carboxylic acid derivative. So what is the polarity of the carboxylic acid derivative? So here in the structure, you can see the carboxylic acid and their derivatives differ by their only by the substance Z attached to the carboxyl carbon as shown in the structure. So the four types of this carboxylic acid derivatives are differ from each other by the substituent, that is your for example, is your Z. So that substituent Z is attached to the carboxylic acid carbon. In case of each carboxylic acid derivative is different. So due to this, there is a difference in the structure. In their structure, so the carboxylic acid and their derivatives have a common group, that is acyl group. So they are having the carboxyl means they are having a common group. So this RCO is attached because from the carboxyl acid, this OH is only replaced from there. So here this RCO part is common to all the carboxyl acid derivatives. So the chemical reaction of those organic compounds containing an acyl group depend upon the nature of bond. So the chemical reactions. So the chemical reactions of those organic compounds. So the chemical reactions of those organic compounds that are containing. So all the organic compounds that are containing this carbonyl carbon, or you can say the acyl group RCO part, is depends on the nature of bond. That what is the nature of that bond which is attached to the substituent. Okay, this acyl group is attached to the different substituent. So what is the nature of the bond that is attachment between this acyl group with this substituent? So here, between the carbonyl carbon of the acyl group and the subsequent jet attached to it. So the nature of bond can be non-polar bond also and the polar bond also. So the organic compounds containing an acyl group. So the organic compounds which are containing this acyl group, which is your RCO, they are called acyl compounds. So they are called your acyl compound, and on the basis of polarity, acyl compound can be classified into two types. So on the basis of polarity, these compounds are divided into two parts, two types, that is a non-polar carbonyl compound and the polar acyl compounds. Again, I'm telling you, due to the polarity of this carboxylic acid derivatives, these are classified into two types, that is a non-polar carbonyl compound and the polar acyl compound. But you can see that the acyl part which is attached to uh, the substituents is the common for all the carboxyl acid derivatives, because structurally the carboxyl acid and their derivatives are differ by only the substituent Z that is attached to the carboxyl carbon as shown in the structure. So in the structure, you can see here that the carboxyl acid and their derivatives are having a different substituent, that is a Z, but they are having the common RCO, that is the acyl group, and the carboxyl acid and their derivatives have a common group, that is your acyl group, RCO, and the chemical reaction of those organic compounds containing an acyl group, depending on the nature of bond between the carbonyl carbon of acyl group and the subsequent jet attached to it. So the organic compounds that are containing an acyl group are called acyl compounds, and so here the chemical reactions. So the organic compounds which are having the same your common group, acyl group, is attached to the different substituents. They are depends on the nature of the bond, whether it is the polar or the non-polar. The bond between the carbonyl carbon of acyl group and the substituent jet attached to it. So the organic compounds containing an acyl group are called acyl compounds. So here the organic compounds which are having this acyl part or the acyl group, they are known as acyl compounds. And on the basis of that polarity, these acyl groups can be classified into two types. Firstly, it is a non-polar carbonyl compound, and secondly, it is a polar acyl compound. So here in the structure, you can see here that RCO in carbonyl compound and the acyl compound both are same, as both are your acyl group, and Z is different. So the bonding is depending upon the bonding between this carbonyl or the acyl group and the Z is classified into two. That means here that bonding may be a non-polar bonding and it can be a polar bonding also. So they are classified into two types of compounds, that are non-polar compounds, non-polar carbonyl compounds, and the polar acyl compounds. Next, the carbonyl group of acyl group in carbonyl compound is attached directly to the hydrogen atom or any other carbon atom. So the carbon-carbon bond and carbon-hydrogen bond are non-polar because the electronegativity of the carbon and hydrogen are always same. For example, aldehydes and ketones are non-polar carbonyl compounds. So the carbonyl carbon of acyl group in carbonyl compound is attached directly to the hydrogen atom or any other carbon atom. So here the carbonyl carbon, carbon of this acyl group in the carbonyl compound. So this is the carbonyl compound. So in this is the acyl group, and in this acyl group, this is your CO, this is your carbonyl carbon, this is your C, is your carbonyl carbon, and in this carbonyl carbon can be attached, is attached directly to the hydrogen atom. It can be attached directly to the hydrogen atom, as you can see here that it is directly attached to this hydrogen atom, and or any other carbon atom. So here it can also attach to any other carbon atom. And the carbon-carbon bond and carbon-hydrogen bonds are non-polar. The carbon-hydrogen bonds are non-polar, and the carbon-carbon bonds are carbon. If there is any carbon here, if a carbon is attached, this is the aldehyde and the ketone. So in this case, ketone, there is a carbon is attached, and in the aldehyde case, there is a hydrogen is attached. So in both of these cases, there is a bonding that is in non-polar bonding. So the carbon-carbon bond and the carbon-hydrogen bonds are non-polar because of the electronegativity of the carbon and hydrogen are almost same. For example, aldehyde and ketones are non-polar carbonyl compounds. So though both of them are the non-polar carbonyl compounds, because in them aldehyde and ketone both are attached. This carbonyl carbon is attached to the hydrogen as well as to the carbon, and the carbon carbon bond and the carbon hydrogen bond both are the non-polar bond because of the electronegativity of between the carbon and the hydrogen. So the carbonyl carbon in acyl compound. So here in case of acyl compound, it's attached directly to an oxygen, nitrogen, or the halogen atom. So here such bonds CO, CN, C halogens are polar because oxygen, nitrogen, and halogens are more electronegative than than that of carbon, and the carboxyl acid and their derivatives are the example of acyl compound. So here the carbonyl carbon in acyl compound is attached directly to an oxygen. So in this the carbon, this is the carbonyl carbon which is directly attached to the halogen atom, oxygen atom, or the nitrogen atom. So these bond, that is your carbon Cl, carbon oxygen, and carbon nitrogen are all of them are the polar bond because of the more electronegativity than the carbon atom, because these atoms are having these heteroatoms are having the more electronegativity than the carbon, than these carbons, and that of the carbon, because carbon is having the less electronegative than the heteroatoms, so they are polar. So the bond between the carbon and the heteroatoms are polar, and the carboxyl acids and their derivative are the example of this acyl compound. Next is the nomenclature of carboxyl acid derivative. So how you will nomenclate these carboxyl acid derivatives? So in case of your acyl chloride, the IUPAC system acid chlorides are named by replacing the E ending of the parent alkane by oil chloride. So in this case, you can see this is the structure of HOCl. So this is the structure of HCOCl. So in this case, there is the common name is formyl chloride. So there is only one carbon in there. So in that case, their name is formyl chloride, and the IUPAC name is your methanol chloride. So this is the first compound of this acyl chloride, in which the E from the E is replaced by the parent alkane, that is your oil chloride. So here in the IUPAC system, it is in this the E is replaced by the oil chloride. So here its name is methanol chloride. So its name is methanol chloride. So CH3COCl, the common name is your acetyl chloride, and the IUPAC name is your ethanol chloride. So in the structure CH3COCl, the common name of this compound is your acetyl chloride, and the IUPAC name is your ethanol chloride. So in that case, the structure CH3COCl. The common name is your acetyl chloride, and the IUPAC name is your ethanol chloride. So the structure of this C2H5COCl, the common name is your propanol chloride. As you can see, there are three carbons attached to this Cl. That is why it is given this prop. So here the IUPAC name is your propanol chloride. So from the alkane, the E is replaced by this oil chloride. So after that, this is your C3H7COCl. So here the carbon that is attached, the carbon that are present in this compound is your 4 carbon atom. That is why its name is your butanol chloride. So its name is butanol chloride. So in case of C4H9COCl, so it is having 5 carbon atoms. So its name is variable chloride, or you can say pantenoid chloride. So according to the IUPAC name is pantenoid chloride. So here the first nomenclature of this carboxyl acid derivative is that in the ethyl chloride, you can see that from in the ethyl chloride, the HOH is replaced by a Cl. So here the chlorine is attached to this, and in IUPAC system, the acid chloride, these acid chlorides are named. This acid chloride are named by replacing the E ending of the parent alkene. Means if there is a methane, then from the methane its E is replaced. E is replaced by the parent alkane. E is replaced by the parent alkane, that is your oil chloride. So this oil chloride is attached to this E. So in the structure, this is your HCOCl, and the common name is your formyl chloride. And in the formyl chloride, you can, according to the common name, its name is formyl, because in the common name we use the form. So here we are using this aryl chloride. So that is why here its name is formyl chloride, and in case of IUPAC, its name is methanol chloride. So in the second, this is a CH3COCl. So here there is 2 carbon atoms is attached to it, and in that there is a formation CH3COCl. So there is a formation of this ethanol chloride. So in this IUPAC name, its name is ethanol chloride, and its common name is acetyl chloride. So from this acetyl chloride, acetyl is in the common name. Acid is common in the common name is given with the carbon 2 carbon atoms. So here in the common name, its name is acetyl chloride, and IUPAC, according to IUPAC, its name is ethanol chloride. So the C2H5COCl is having the 3 carbon atoms, and its name is propanol chloride, and IUPAC name is propanol chloride. So in this structure, in the C3H7COCl, its common name is your butyryl chloride, or IUPAC name is your butanol chloride. And in this C4H9COCl, its name is your beryl chloride, and the IUPAC name is your pantenoid chloride. So next is your acid anhydride. So in the acid anhydride are named by adding anhydride after the IUPAC name of the acid. So acid name is your or oic acid. So in the common name we are using this oic acid. So from here the acid is replaced by your anhydride. So here you can see this is your CH3COO, CH3CO. Its name is your ethanoic anhydride, because here the 2 carbons is attached each to the oxygen atom. So that is why we are naming it ethanoic anhydride. So its name is your ethanoic anhydride. So next is your CH2CO, OCH2, C2H4, and C2H4, and its name is your succinic anhydride. So in this case, its name is your butene dioic anhydride. Next is your benzene ring is attached to the 2 carbon and the 1 oxygen. That's name is phthalic anhydride. So its name is your phthalic anhydride, and according to the IUPAC name, its name is O-benzene dioic anhydride. So in the benzene, on the ortho position, the two dioic groups are attached, means these two carboxylic acid groups are attached. That is why its name also benzene, oic, dioic anhydride. Now it's the acid ester. So in the acid ester, you can see in IUPAC system, the esters are generally named by first naming of the alkyl group followed by the name of the acid and changing the ic by 8. So here in this, from the acid means carboxylic acid, the ic means carboxylic, oic. So from the OIC, the IC is replaced OIC. From the OIC, this IC is replaced by the A. So in this acid esters, so here first is the HCOO, CH3. So in this also methyl formate, because here to this oxygen atom, both the side one oxygen is present. So that is why its name is methyl methonate. So methyl methonate. Next is a CH3COO-C2H5. So in this case, its name is ethyl ethonate because both sides of this oxygen atom, there is two carbon atoms are attached to this oxygen atom, and its name is ethyl ethonate, and its common name is your ethyl acetate. But in the common system, we are taking this one ethyl group as a substituent. That is why we are using here ethyl acetate. Next is your structure, that is your C2H5COO CH3. So in this we are giving methyl propionate. So its name is methyl propionate. So in this case, methyl propionate. Next is your CH3COO C6H5. Name is your phenyl acetate because one side phenyl group is attached. So here its name is phenyl ethylate. So and the second carbon is from the left, you can see that this is the CH3COO-H5. So H5 is acting as a substituent, is attached to the CO group, and a CH3CO is the main. So here we are using as a suffix, so its name is phenyl ethonate. Next is your C6H5COO C6H5. So this is your phenyl benzoate, and in this phenyl benzoate its name is same. So here next is your C6H5COO-CH3. So its name is CH methyl benzoate, because here now we are considering this CH3 as a substituent, and this is the main group. So that is why its name is methyl benzoate. Next is your amide. So in the case of amide, the E from the alkane is replaced by the amide. So here its name is HCO NH2. So in this, its IUPAC name is your methanamide. So in the CH3CO NH2, its name is ethanamide. Next is your C2H5CO NH2, its name is propanamide. C3H7 is having the 4 carbon atom, that is why its name is propanamide. And C4H9CO NH2 is having a 5 carbon atom, its name is pentanamide. Then the relative stability of the acyl derivatives. So the acid derivatives can be listed in order of the reactive order towards nucleophilic acyl substitution, as it is acyl chloride having a high relative stability, then acid anhydride, then ester, then amide. So the magnitude of the delta plus charge on the carbonyl carbon depends on the electron releasing or electron attracting power of the substituent, and the substituent group of acid chloride and acid anhydride have an ability to withdraw electrons from the carbonyl carbon, making this derivative more reactive than carboxyl acid. On the other hand, in ester and amides, the subsequent Z group releases electrons onto the carbonyl carbon, which makes this derivative less reactive. The reactivity of the carboxyl acid derivative can be explained in detail as the acyl chloride, the electron withdrawing inductive effect of the acyl chloride is not stabilized by the electron pair donation, and the electron withdrawing inductive effect of the chlorine making more electrophilic and more reactive towards nucleophilic acyl substitution. In case of acid anhydride, the carbonyl group is better stabilized by electron donation, Then acyl chloride. So here electron pair orbital of oxygen overlap with the orbital of carbonyl group, but the presence of two carbonyl groups create competition for the same electron. So thus the extent of stabilization in resonance is decreased. So next is your ester. So in the ester, there is stabilized. These are more effectively by the electron pair of oxygen than the acid anhydride, because only one carbonyl group is present in ester, and this increases the stability of carbonyl group of ester and decreases the reactivity towards the nucleophilic substitution than the acid anhydride. In case of amides, in this the acid amides are less reactive towards nucleophilic substitution, and this is due to the positive charge on acyl carbon atom, which is so necessary for nucleophilic substitution, and they are at least 10 times less reactive than acyl chloride. Now the question, which function group is present in the carboxyl acid, that is the A, which of the following is the ester, that is your B. Next, acyl chlorides can be obtained by D from carboxyl. Acyl chloride are more reactive than other carboxylic acid derivative due to the electron withdrawing inductive effect of chlorine atom. And when propanoic acid is treated with the aqueous sodium bicarbonate, then there is a formation of this bicarbonate group. So there, C of the CO2 comes from the bicarbonate group, and the benzoyl chloride is prepared from benzoic acid by is SOCl2. On reaction with NH3, acid chloride forms amides, and the acetamide is treated separately with the following reagent, which these would give methylamine, that is the NaOH plus Br2. These are the references from this topic. You can study this topic from these books. Thank you so much for today's lecture.